Hey there, wanted to let you know this is an audio only podcast, and if you get your podcast on Spotify, you can go follow me there. All right, cheers. Welcome back, ladies and gentlemen, to the Ephemeris Podcast, your weekly astronomy podcast. I'm your host, Aphelion, and if you're not familiar with the structure of our episodes, and if you are a new viewer, every single week we have an episode where we get into some articles that talk about news in the world of astronomy. And so for this week, we have two articles rather than three. I know I usually go with three, but our first article today is going to be quite lengthy. So I decided to make it two articles for this week. The first story is about a possible Einstein telescope. And then our second story is going to be a little bit shorter, and it's going to be about the visibility of the universe and some questions regarding that. So let's start out with this first story, um, which is about a possible Einstein telescope in the future. Now, the name would suggest that it's a space telescope. It's not. We will get into the details of that in just a minute. But let's introduce our topic here. So, we've talked about the past, present, and future of telescopes here and there on this podcast. We've mainly been talking about space telescopes recently with like Spitzer, Chandra, Hubble, all of those famous and notorious telescopes that have been out in space, sort of scanning the universe in all parts of the electromagnetic spectrum. We've talked about some future plans like UVEX, and we've got some more news on some future projects. Now, this one isn't going to be a space telescope. It's actually going to be a ground telescope, or maybe even an underground telescope, I should say. So let's welcome to the stage here the Einstein Telescope. So it's been proposed as a part of a plan to create more efficient gravitational wave detectors. And the namesake is obviously Albert Einstein, who created one of the most influential astrophysical theories, that is the theory of general relativity. And it actually predicts gravitational waves, which is what this telescope is meant to detect. So, to understand what the technology for something like this looks like, we should probably have a look at some of the current observatories that do gravitational wave detection, and the most famous of them would be LIGO, or also known as the Laser Interferometer Gravitational Wave Observatory. So, yeah, it's probably one of the most notorious. I'm just going to preface this by letting you know that a lot of what I'm going to talk about here is the nitty gritty about the technology that exists within LIGO and how exactly the interferometer works. So, if you're already familiar with it or are not very fond of all of the details and whether they relate to this story or not, you can feel free to skip ahead. I will try to put some timestamps here, but I want to talk about the technology behind LIGO because it's going to be important when we talk about the Einstein Telescope and what exactly it's improving compared to something like the LIGO. So, yeah, that's the reason why I'm going to do a bit of an in-depth explanation here. So let's not stall that any further. So, LIGO is a large-scale physics experiment, and when I say that, I mean it, because the arms of the detectors are long. They are 4 kilometers long, and the area of the actual observatory and the fact that there are actually two interferometers like 3,000 kilometers apart, this is definitely a large-scale physics experiment. So what exactly does it do? It detects ripples in space-time, which is exactly what gravitational waves are. And where we expect to detect this is from extreme cataclysmic events like neutron stars colliding or even black holes colliding that are like typically 1.3 or 1 billion light years or more away from us and usually shrink down to a small intensity by the time that they get to us. And the instrument that's used for this detection, as the name suggests, is an interferometer. I talked about the observatory being in multiple locations. The type of interferometers that we are talking about here, they're at the basis, Michelson interferometers. Hopefully, I'm saying that correctly. I'm not very good with names, but yeah, Michelson interferometers is how I'm assuming it's pronounced, but feel free to correct me in the comments. So what these interferometers are, they're known for their L shape, and this is a shape that the observatory resembles. There's a beam splitter at the vertex of the L, which sends light down both arms, and then that light is usually immediately reflected back to the beam splitter, and then there's like a fringe that is created and measured by a detector. But LIGO improves on that idea by adding two other mirrors that causes the light to bounce around 300 times within the arm before recombining. The reason why that's done is because the LIGO has to produce a significant amount of power to be able to detect changes in light that would be caused by a gravitational wave. And I think there is something about is it the wavelength? Perhaps not, but I think there's another factor also that requires that the light bounces several times. So there are more complex ways in which LIGO is a little bit different from a basic Michelson interferometer, and I'll talk about what the detection method produces in just a second when we actually detect gravitational waves. But yeah, let's talk about some other things here. It's not effective for scientists to plant a larger-than-life Michelson interferometer in the middle of the Earth and just call it a day, because gravitational waves, when we receive them, they have a very minute intensity, like I talked about. And so if you have some other kinds of vibrations that occur in the whole system, the whole detection method is a bit illegitimate. So you have to go the extra mile to ensure that, the detector doesn't pick up any non-gravitational wave vibrations. And the way that they do that is they make sure that the mirrors, or they call it test masses because they're testing for gravitational waves, they have to make sure that those are absolutely still. And to do that, firstly, the mirrors reside at the end of a series of complex mechanical vibration isolation systems designed to make them feel like they're floating in space. And this is a description according to the LIGO website. So to break that down into more simpler terms, because that's a lot to digest, basically the system that keeps the mirror from experiencing vibrations is a 4-stage pendulum system. So you have several simple pendulums that are inserted into the system, and they're kind of like stacked on each other. So whenever a non-negligible amount of vibration arrives at the system, it must pass through one pendulum, which absorbs some of the energy of the vibrations, but then, it utilizes the law of inertia, and it creates like sort of a, I guess you call it equal and opposite reaction from the next pendulum, and that absorbs energy, and it's kind of like a chain before you get to the actual mirror, which usually experiences like a very, very tiny fraction of that vibration, like 1/1,000,000th or something like that, which is completely insignificant. So yeah, combined, this structure is so effective at reducing vibrations that at any present at the top of the suspension are made 100 million times smaller by the time they reach the test mass itself. So yeah, what I just talked about. And this is a quote coming from the LIGO website again. So before that's even happened, that whole process, there's a larger structure that removes vibrations that are caused by things like earthquakes, traffic, or even the tides. And it's called an active isolation system. And it kind of does a thing similar to noise-canceling earphones. If you're not familiar with noise-canceling technology, basically what it does is it senses the longitudinal sound waves that are like reaching something like your headphones, and it sends an inverted version of those waves, which causes what is known as destructive interference. And so essentially this is kind of what active isolation the active isolation system is doing, but instead of dealing with longitudinal waves, it's probably dealing with surface waves, which that's my guess, and yes, that's the name for it. And it does this detection method through seismometers, and it sends the information to a computer, which sends the inverted waves using hydraulics. And yeah, that will just cancel out any external vibrations before they touch the pendulum. So that's the first part of maintaining the mirrors, and then you have to be extra careful to get most of the light reflected so that any minute vibration caused by the mirrors and splitters is detected. So this is done by making the test masses out of ultra pure materials that are laid down in nanometer thick layers. And they're coated with coatings that reflect all but one of every 5 million photons that hit them. So very, very efficient at reflecting light and getting that, power that you need. And so, yeah, with all of that amazing technology, how exactly are we meant to know that gravitational waves are detected with this, crazy apparatus? Because of the pristine condition of all of the components, which we've, guaranteed with all of the technology we had before, we would expect all the light that is sent through the beam splitter to the arms and sent back ends up canceling each other out by the time it reaches the detector. So again, destructive interference. The observatory maintains an ultra-high vacuum to make sure that none of the light gets scattered in any way, and there's no issues with that. And they want to make sure that nothing but the gravitational waves will cause light to sort of not have destructive interference. And so when a gravitational wave does show up, what happens is it causes the arm to oscillate in length, which will cause the phase of the light when it reflects to change. So that means that instead of the light from both arms being sort of in sync, they're actually out of sync, and that will create constructive interference instead of destructive interference. And once we see the constructive interference on the detector, we will know that light's appeared and we've noticed a gravitational wave. So that's how you detect the gravitational waves exactly. So yeah, that's the technology, that's the whole method behind the madness that is gravitational waves, and definitely a long explanation. But again, I wanted to illustrate a point that there are a lot of extra steps that need to be taken to detect gravitational waves if you are to do it on the ground, on the surface. And the primary focus of making these adjustments is to create an environment more like space, rather than being disturbed by things that exist on Earth. So that's the exact reason why we would need something like the Einstein Telescope. So here's where we get into the new stuff. The idea is to create a new detector that does LIGO's job, but better by adjusting a couple things. Firstly, and I'm taking a bunch of quotes that are off of the article because they do put it really well. The Einstein Telescope will consist of 3 nested detectors. Each of these detectors will have 2 laser interferometers with 10-kilometer long arms. In order to shield as much interference as possible, the observatory shall be built 250 meters underground. And just by logic, makes a lot of sense when you put it underground, less disturbances that you have to protect the test masses from. Creating the 10-kilometer long arms means that the light has to actually reflect less to get the same power that LIGO does. So this would be a great adjustment. And I guess 3 nested detectors, will get into exactly why you need that in just a second. 2 laser interferometers, I'm not sure, but I'm assuming it's a very significant upgrade. Another thing here about what the Einstein Telescope is expected to do. Quote, "We want to use it to examine an area that is 1,000 times larger than what is possible today in the universe for gravitational waves. And we should then find considerably more sources for which the current instruments are not sensitive enough," explains Professor Stahl, a member of the German Einstein Telescope community. This also applies to heavier objects that emit gravitational waves at lower frequencies. So here's just kind of pointing out that Sometimes the sensitivity of a LIGO or any similar gravitational wave detector is not enough to examine some areas of the universe, and there are some frequencies that um, LIGO's just not suited for. So another thing that was mentioned is that the Einstein Telescope will work together with a new innovative generation of observatories in the electromagnetic spectrum ranging from radio to gamma rays. We call this multi-messenger astronomy. And yeah, that's something where you have to consider how it's different from LIGO. LIGO is basically blind. It does not look at any parts of the electromagnetic spectrum when it's detecting a gravitational wave, but there's a lot more to a cataclysmic event in the universe than just um, the gravitational wave part of it. There will be the gravitational wave, then you will receive multiple parts of the electromagnetic spectrum, um, sort of signals from them, radio, visible light, optical wavelengths, and all of that stuff. And then, you get the whole picture once you get that, not just the gravitational wave. And so when you have all of those things together, it makes the process a lot more sort of put together, I guess. And that's what the Einstein Telescope is looking to do. Based on a lot of the things that I've said here, you might notice that it's quite optimistic and idealistic from what we see here because, I mean, logistically speaking, building 10-kilometer long arms 250 meters underground is quite a task. And, it isn't something to be taken lightly, obviously. So, in that way, very optimistic and idealistic. LIGO's arms are only 4 kilometers in length, like I think I've already mentioned. So, yeah, and I've already talked about how, like, LIGO cannot do some of the things that the Einstein Telescope is striving to do. LIGO admits, that to find a possible light source associated with a gravitational wave detection, you need multiple instruments, and you have to be able to detect the signal to localize the source on the sky. So, yeah, really cool ideas that we have with the Einstein Telescope. I'd love to see if this idea gets developed in the future. And it could make gravitational wave detection a lot bigger of a subsect in, I guess, astronomy. So, yeah, that is the first story. I know, quite long. That is exactly what I intended to do. 2 stories because I thought it was interesting just looking into what exactly goes behind some of these huge observatories and what's so special about them, and then talk about maybe possible improvements. So yeah, with that out of the way, let's get into something a little bit lighter, not too in depth, just a interesting question to pose for our understanding. How can the visible universe be 46 billion light years in radius when the universe is only 13.8 billion years old? This is a fact that I don't think I've mentioned many times on the podcast, but it was a fact that I was vaguely aware of, and it's a question that actually piqued my interest once I'd seen it in an article because it was always in the back of my mind, but I never looked to answer it. So here is my golden opportunity. We know the universe is 13.8 billion years old. We've mentioned that fact a couple times on this podcast before. I'm not going to get into depth about the whole number because that involves explaining the evolution of the universe, as I've done several times in, a little bits before. So, yeah. So 13.8 billion years old, the age of the universe. But we describe the length of the observable universe to be 46 billion light years, according to this article. So how is this possible? Well, it has to do with the nature of the expansion of the universe. The universe isn't limited to expanding at the speed of light, or at least, seeing light travel relative to us. The speed of objects in the universe are limited to it, but not the universe itself. Another thing to note is that we can't put a number on the expansion speed of the universe because, firstly, it has no reference. We don't have anything to use as reference for the universe. And secondly, because our best efforts have led to separate numbers depending on where you look. And we've talked about that before. So, based on this 46 billion light years a number, we're assuming that the universe is expanding faster than the speed of light, as we see it. So, if that's the case, how are we able to know that the universe has done this? There's a lot of uncertainty about the expansion of the universe. How do we, know for certain that it's exactly this much? The universe has expanded exactly this much faster than light has traveled. Well, that has to do with Hubble's expansion law. So the further an object is, the faster it's traveling away from us. And this means that the object has gone farther than we see it by the time its light has reached us. And that's where we get our answer. We observe light coming from nearly 14 billion light years away from objects that have moved substantially since the light was emitted. And the exact number would be like the difference between 13.8 and 46, which is going to be about 32 billion light years. So yeah, with calculations, we figure out that the objects emitting the earliest light have made it, in a total of 46 billion light years away from us. For some, this is a sufficient answer because, if you get it conceptually, maybe that's enough for you. But you might be curious as to what kind of calculations could be used to get such a number because it does seem like a very vague subject. My guess is that the equations relating to the relativistic Doppler effect are used in this process. Just briefly, the relativistic Doppler effect describes the change in frequency, wavelength, and amplitude of light caused by the relative motion of the source and the observer. But instead of simply measuring the difference in wavelengths emitted and observed from an object to just calculate redshift, you go further and you use that redshift to calculate recessional velocities of an object, and that would be relative to us. And once you have that number, you would then be able to predict the distance an object has traveled since receiving its light. So, yeah, that's my guess as to how exactly they ran the numbers on it. But conceptually, the idea is just that we know the universe, like the observable universe, has expanded to a maximum of 46 billion light years because we received its light from nearly 14 billion years ago, and it has traveled a lot farther since we've received that light. So that's a very sort of watered down answer for a interesting question that, sometimes might seem, obvious, but isn't quite. And that's all I've got for today's episode. If you all enjoyed listening to these two stories I had here today, thank you, first of all, for making it to the end of the podcast episode. If you enjoyed it, again, make sure to drop a subscribe on the YouTube channel if that's where you're listening. And if you're listening on Spotify, then go ahead and drop me a follow. But until next week, I will see you all later. Peace.